And in the case of the square root property of equality, and this is going to state, and again, this is a different approach from taking what we have with the zero product property. And say if you have the square of an expression set equal to a value. Say like they have x squared is equal to p. If I go from the square of the expression represented by x, we're going to have going out to first order. In this case, say we have first order in x, we have just x, and that's going to be equal to plus or minus the square roots of p. And drawing separately, so we have the square root of p as well as its additive inverse, where we have the negative of the square root of p. And let's say that, just kind of taking what we have among examples. And say if you're looking at solving by the square root property of equality, and I just call this SRP. And say we have like x squared is equal to 4. Okay, so you're solving for x, and we have x squared is equal to 4. Now, you could set this up as quadratic equation, standard form, have like x squared minus 4 is equal to 0, and then factor as x plus 2 and x minus 2, and utilize the zero product property. But if I go with the square root property of equality, so you have x squared laid out, p is represented by 4, and if I go from the square of x to just x, well, x is going to be plus or minus the square root of 4, and in compact terms, our solutions in x will be plus or minus 2, and itemizing, okay, we have x is equal to negative as well as positive 2. Right. And now, let's say that if we have more than just the square of a single term, and we'll say that we have the square of x plus 1, and say that is equal to 49. Okay. All right, so you have x squared represented by the square of x plus 1. Now, if I were to go from this stage to that one, so if I go from the square of x plus 1 to just plain x plus 1, and for plus or minus the square root of p, this would be plus or minus the square root of 49. So you have that x plus 1 is equal to plus or minus, and with 49 as a perfect square number, we have x plus 1 is equal to plus or minus 7. And if I separate, now we're still solving for x. Now one value of x is going to be whereupon x plus 1 is equal to negative 7. The other whereupon we're going to have the x plus 1 is equal to positive 7. So for x plus 1 equal to negative 7, if I take 1 away, we're going to have the x is equal to negative 8. If on the other hand we have x plus 1 is equal to 7, we're going to have the x is equal to 6. And you can go back and check. Now we have negative 8 plus 1 is negative 7. The square of negative 7 comes out to 49. As for 6, 6 plus 1 is 7, and 7 squared is equal to 49. So both of these apparent solutions do check out. And in terms of notation, I'll use this as kind of a springboard to where we have irrational roots. And let's say that if I have the square root of x minus 2 is equal to 15. Okay, and so we're going to have, in this particular situation, so we have, again, just like at this stage you had the presentation, you have like x squared is equal to p. And if I go from x squared to x, not ready to put the number down yet. So you have x squared to x. Okay, so you have x is equal to plus or minus, okay, the square root of p. Okay, so going from the square root of x minus 2 to just x minus 2. So giving up or sacrificing the 2, that's is going to translate on the other side as taking the plus or minus the square root of that value. So right now we have x minus 2 is equal to plus or minus, okay, the square root of 15. And what I want to do here, okay, if you notice, you have x minus 2 equal to plus or minus the square root of 15. And I'm still solving for x, but what I'm going to do here, just kind of give you a compact notation. And I'm going to do a bit of horizontal adding in this case. So I'm just going to create a bit of space here. We're going to have the plus or minus the square root of 15 to follow the constant that is added or subtracted. Now for x minus 2, if I translate this to just x, I'm going to add 2 to both sides. So negative and positive 2 are additive inverses. So you're going to have the x is equal to 2 plus or minus the square root of 15. And if you itemize the results, so you have x equal to 2 plus as well as 2 minus the square root of 15. Now with the other groups, okay, I did not put this up yet, but if you have, let's say, the square root property of equality, I'm just going to go back to x. Well, let's say if you have something like x squared is equal to, let's say is equal to 75. Okay, and like x squared equal to 75, kind of like x squared is equal to 4. And if I go from x squared to x, so x would be plus or minus, okay, the square root of 75. Now, 75 is not a perfect square number, just like 4 from earlier. But it is one of those radicals that can be reduced, okay, unlike what we had a moment ago with 15. Now, what I mean by radical reduction, now we have for the square roots of 75. Okay, like you have with your perfect squares. You have like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 times 6, 7 times 7, and so on. Now for the number 75, now the highest perfect square that will go into 75, that is going to be 25. And 25 into 75 will be 3 times. So in taking what we have now, so square root of 75, we have square root of 25 times the square root of 3. Square root of 25 is 5 and we have times the square root of 3. And so it's going to follow that for the solutions in X. Now they're going to be additive inverses, and for the reduced radical form. Okay, so you're going to have plus or minus 5 times the square root of 3. And placing in itemized terms. So you have 5 times the square root of 3 as well as the negative of 5 times the square root of 3. From the standard form of the quadratic equation, the outcomes would be what you would have in the development of the quadratic formula. And for the quadratic formula, this is going to be where we have x is equal to negative b plus or minus. Okay, and have the square root of b squared minus 4ac we have all over 2a. Again, so we have for a, okay, again, you have a non-zero valued constant. And now, in the case of what we have with the quadratic formula, and just kind of give you a couple of cases here. Okay, and we'll say that we have as a first case. Now start out where all the terms are going to be positive. And we will say that we have 2x squared plus 7x plus 1 is equal to 0. Okay, so we're going to have here now, one might try to factor 2x squared plus 7x plus 1, and it might be factorable, but it will not be in the context of integer values, because the only thing we have here is that if you try to factor by grouping, let's say you have the first times the last coefficients, which are going to be 2 and 1, the product is going to be at 2, and then trying to find factors of 2 that will add up to 7, and you're not going to have integer factors, because the only integer factors will be 2 and 1 and negative 2 and negative 1, and the sums will be at 3 and negative 3, but not 7. But we do have a bit of a recourse, because we have a quadratic formula approach, and the equation is a standard form. And looking at the layouts, okay, so we have representing a is the leading coefficient 2. And bx, we have represented by 7x. Okay, so we have that b is equal to 7. And plus c, okay, so we have that c is equal to 1. And you can use a quadratic formula regardless of whether the trinomial is factorable or not. Now, for what we have in the case of the quadratic formula, so we're going to start out with substitution into those numbers representing a, b, and c. Okay, so just initiating the process. Okay, so we have a negative b, so you have the negative of 7. Then we have plus or minus, okay, the square root. Now for b squared minus 4ac, okay, so we have 7 squared minus 4 times 2 times 1. And we have all over 2a, so that is going to be 2 times 2. negative 7 plus or minus. Now for 7 squared is 49. And for negative 4ac, so we have negative 4 times 2 is negative 8. Negative 8 times 1 is, again, minus 8. And 2a, we have it 2 times 2, which is going to be 4. And so for what we're going to have, we're going to have it negative 7 plus or minus, okay, the square root of 41 all over 4. And in terms of just itemizing, so we're going to have at the upper end, we have negative 7 plus the square root of 41 all over 4, as well as negative 7 minus the square root of 41 also over 4. Okay, now another case here, and this is where you had to be careful with the quadratic formula should you go that route. Now mainly we'll get the negative b, the 2a, and the b squared right. It's where you have the minus 4ac, okay, that careless mistakes can occur. And let's say that just a little bit of a change up. If I have, let's say, and it's almost the exact same equation, but this time I have 2x squared minus 7x plus 1 is equal to 0. Okay, so we have a little bit of history to repeat. Now we have for a, okay, so once again we have that a is going to be equal to 2. Now for b, okay, now b, not positive 7, but negative 7. And we have that c is equal to 1. So in taking what we have for x, okay, so we have with negative b, and applying direct substitution, so I have the negative of minus 7, then we have plus or minus, okay, the square root. Now for b squared, okay, so we have the square root of negative 7 minus 4ac, so you have minus 4 times 2 times 1 again we have all over 2a, so that's going to be 2 times 2. Right, it looks like we'll have a lot of similar history to repeat. Now the difference this time around is that we have in the substitution, okay, we have b at negative 7 as opposed to positive 7. But now for negative b, now b is already at negative 7, and so we have the negative of negative 7, that is going to be a positive 7. Now the square of negative 7 is going to be, once again, a positive 49. And negative 4 times 2 is negative 8, times 1 is still negative 8. We have all over 4. And this time we have for the set of solutions, we have positive 7 plus or minus, okay, the square root of 41 all over 4. And again, if you itemize, so you have 7 plus the square root of 41 over 4, and 7 minus the square root of 41 also over 4. Tell you what, just in terms of the quadratic formula, just for the next few moments, let's see what we get in terms of solving for x. Where we have 2x squared minus 9x minus 1 is equal to 0. And this is a trinomial that cannot be factored into integer terms. So let's see what we get for x from 2x squared minus 9x minus 1 is equal to 0. Alright, for this equation, for 2x squared minus 9x minus 1 is equal to 0, again, this is another trinomial that we cannot factor in terms of integer coefficients exclusively. And if we go with the quadratic formula pathway, so again we have a is going to be represented by 2. And from negative 9x minus 1, this time we'll have b is at negative 9. And c is going to be at negative 1. And so, in the reapplication of the quadratic formula, so we have for negative b plus or minus the square root of b squared minus 4ac all over 2a. So for negative b, we're going to have the opposite sign of negative 9 plus or minus. Okay, we have the square root. Now for b squared, we have the square of negative 9. Okay, now again for the minus 4ac part, okay, had to be careful. So you got minus 4 times a, which is 2, times c, which is now going to be negative 1. And we have all over 2a, again, which we're going to have at 2 times 2. Now after the substituting, okay, so you have negative b, so you have the opposite sign of negative 9, so this will be a positive 9. Yeah, plus or minus, now the square of negative 9, okay, that's a positive 81. Now for the minus 4ac, we have negative 4 times 2 is negative 8. Now we have negative 8 times negative 1 is going to be a positive 8. So we're now adding 8 as opposed to subtracting 8. We have all over 2 times 2, which is going to be 4. And for the results here, we're going to have 9 plus or minus, okay, the square root of 89 all over 4. And that'll be the compact solution. And again, you can draw out separately. Itemizing, okay, so we have on the upper end we have 9 plus the square root of 89 all over 4, and at the lower end we have 9 minus the square root of 89 over 4. And we'll say that we have here and let's see. Let's say we have 3 minus, and so we'll say we have 3 over 3 plus 4 over So you have 3 plus 4 over x plus 1 is equal to, let me do this way. I was just saying something. Yeah. We'll say you have 3 plus 4 over x plus 1 is equal to 5 over x. Okay, so you're looking at solving for x, whereupon we have 3 plus 4 over x plus 1 is equal to 5 plus x. Now, let me mention some things here. Now, there was something from the other exercise where we had at the start restricted values. Now, whatever we have for x, okay, we cannot have zero value denominators. Okay, so just kind of as already as a precondition, now we have that x plus 1 cannot be 0 and that x cannot be equal to 0. So we have here, so we've got the restrictions. X cannot be -1, and the x cannot be at 0. In other words, you don't want 4 over -1 plus 1, which will be 4 over 0, and at the same token, we do not want 5 over 0. Now for what we have here, we can clear out the fractions with the least common denominator. Okay. Least common denominator, we're going to have the product of x and x plus 1. And in setting up, okay, what we have here, if we multiply all the terms out by x and x plus 1, so we have, just for starters, now we already have 3, we have times x, times the quantity of x plus 1. And again, multiplying by the least common denominator. Okay, if you notice, okay, now we're not writing all the fractions in terms of least common denominator. We're going to clear out the denominators, because we're dealing with an equation as opposed to combining fractions or terms together. Okay, so with what I have for the first, okay, I have 3x all over x plus 1. So this would be 3x squared plus 3x. And for the next, okay, you're going to have with 4 over x plus 1 times x plus 1. Now you're going to have x plus 1 to cancel out. So you have plus 4x. And for 5 over x times x times the quantity of x plus 1. Now we're going to have x's are going to cancel out, but we still have 5 times the quantity of x plus 1. And working with what we have now, so you got 3x squared, 3x plus 4x, okay, so this will become 7x. And for 5 over the quantity of x plus 1, so this is going to be 5x plus 5. just going to write this again. I'm going to set this up as a quadratic equation that is in standard form. So I'm going to move the 5x as well as the 5. And so for what we will have now, okay, so you have 3x squared. You have 7x minus 5x, so this will become 2x. Okay, now we've got 3x squared plus 2x minus 5 is equal to 0. Now I'm going to sort of bypass the factoring by grouping, but just in terms of factoring. Now for 3x squared, this is going to go to 3x and x. And for what we're going to have here for factors that we're going to have to be present. Okay, so we got in this one, so it looks like the way this is going to turn out. I'll do it. Do have just enough time on this in case you have 3x squared plus 2x minus 5. If I factor by grouping, so you got 3 times negative 5 is negative 15. Now looking for factors of negative 15 whose sum will be at positive 2, but right now it had 3 and negative 5. Now 3 and negative 5, okay, those will combine to negative 2. However, if I change the signs, so I have negative 3 times 5, that will be a positive 2. And we have upon splitting up, so we have 3x squared minus 3x plus 5x minus 5. And we have with grouping first 2 terms and the last 2 terms. So we have the greatest common factors, 3x squared minus 3x, have greatest common factor is going to be at 3x. And into 3x squared minus 3x, I'm going to have x minus 1. Bring down the plus. Greatest common factor of 5x minus 5, that will be 5. And we have times the quantity of x minus 1. So we're going to have, for this result, for the factorization, we're going to have x minus 1. As well as the quantity of 3x plus 5. Okay, so this is what we have here. So for the factorization, just carrying over, so you have 3x plus 5, and the quantity of x minus 1 is equal to 0. And utilizing the zero product property, if I have the 3x plus 5 is equal to 0, so I'm going to have that 3x is equal to negative 5. And if I divide by 3, so I'm going to have that x is equal to negative 5/3. And we have with x minus 1 equal to 0. Now we're going to have an apparent solution with x equal to 1, and the preconditions having to be that x cannot be -1 or 0, and so these will check out. So we have x at -5/3 and also +1.